Welcome to section 3 of the RAG Mastery Playbook. In this section, we will explore what is document ingestion and why it is the foundation of every RAG system. Why AI cannot search raw documents directly. What is chunking and why it is critical for accurate retrieval. What is embedding and how they convert meaning into numerical representation. What is semantic search and why search by meaning is far more powerful than searching by keywords. By the end of this video, you will understand where RAG actually begins and why the quality of document ingestion determines the quality of the entire system. Let's begin. Imagine you are building an AI assistant for your company. You want it to answer questions about company policies, HR guidelines, research paper, technical manuals, contract, and thousands of internal documents. So naturally, all of these documents become the knowledge that AI must learn to access. Now imagine an employee asks a simple question: what is our enterprise refund policy? The answer already exists somewhere inside your company's document. But here is the real question: how does the AI find that answer? Does it open every PDF and start reading from page 1? Does it search through every email one by one? Does it load thousands of documents into memory every time someone asks a question? Of course not. That would be extremely slow, incredibly expensive, and practically impossible. And that is where many people misunderstand how RAG operates. Most people think that retrieval begins when a user asks a question. It does not. Retrieval actually begins much earlier, when documents first enter the system. Before the AI can answer even a single question, those documents must be prepared such a way that computer can search efficiently. That preparation process is called document ingestion. And in many ways, document ingestion determines the quality of the entire RAG system, because if documents are prepared poorly, the retrieval will be poor. And if retrieval is poor, even the most powerful LLM will generate poor answer. So before we understand how retrieval operates, we first need to understand how documents are transformed into something that AI can actually search. And that is where real engineering behind RAG begins. Now let's understand why AI cannot search raw documents directly. Now that we understand what document ingestion is, let's look at the next challenge. A very natural question follows: why can't we simply take all of our company documents and let AI search them directly? After all, modern AI models are incredibly powerful. They can write code, analyze contract, summarize research paper, pass professional exam. So why can't they simply read every document and answer question from them? The answer is surprisingly simple, because AI cannot see everything at once. To understand why, imagine walking into a massive library, not a small library, a library containing millions of books. Now imagine someone asks you a question: what is our enterprise refund policy? The answer exists somewhere inside that big library. Now, would you start reading every single book from beginning to end? Of course not. That would take days, months, and even years. Instead, you would first narrow down where to look. You would identify the relevant section, then the relevant shelf, then the relevant book, and then the relevant page, and finally the paragraph containing the answer. Humans naturally filter information this way. An AI system faces the same challenge. The knowledge exists, but the model cannot process everything simultaneously. And that limitation comes from something called the context window. You can think of context window as if the AI's working memory. Everything the model can actively see while generating an answer must fit into this window. If information is outside the window, The model cannot directly use it that moment. Now, let's think about a real enterprise environment. A large company may have thousands of policies, 10,000s of reports, years of meeting notes, research paper, contracts, technical documentation, support tickets, emails, and countless other knowledge sources. Together, this can easily amount to millions or even billions of records. Clearly, all of that information cannot fit into a single context window. Not today and probably not anytime soon. So, even though the information exists, the model cannot simply load everything and search through it whenever someone asks for a question. That would be computationally expensive, slow, and highly inefficient. Instead, the system needs a way to identify only small pieces of information that are likely to be relevant, not the entire library. So, just the few pages that matters here. This is one of the most important ideas in retrieval-augmented generation. The goal is not to retrieve everything, the goal is to retrieve only the right information. But that creates another challenge. How do we break enormous documents into smaller pieces that can be searched efficiently? How small those pieces will be? And what happens if we break them incorrectly? That brings us to one of the most important concepts in modern RAG system, chunking. And as we will discover that the quality of chunking often determines the quality of retrieval itself. Now that we understand why AI cannot search the entire documents directly, the next question is obvious. What is chunking? At its simplest, chunking means breaking a large document into smaller, meaningful pieces that can be searched independently. That's it. Instead of treating a 300-page document as one giant block of information, we divide it into multiple smaller sections. It sounds simple, but as we will discover, we will see that chunking is one of the most important engineering decisions in any RAG system, because retrieval can only be retrieved what has been stored, and what gets stored depends entirely on how the document was chunked. So now we know what chunking is, and that leads to another question. Why do we need chunking? Imagine your company has a 150-page employee handbook. Inside that, there are chapters about leave policy, work from home guidelines, travel reimbursement, employee benefits, performance reviews, code of conduct. Now imagine an employee asks, what is our work from home policy? The answer certainly exists, but if the entire handbook is stored as one huge document, the retrieval system has to deal with hundreds of pages of unrelated information. Finding one answer becomes difficult. So instead, the handbook is divided into logical sections. One chunk may contain leave policy, another may contain benefits, another may contain work from home guidelines. Now the system retrieves only the relevant chunk, not the entire handbook. Retrieval becomes faster, more efficient, and far more accurate. But now another important question appears. What makes a good chunk? A good chunk is not simply a fixed amount of or number of words. A good chunk represents a complete idea. It preserves meaning. It keeps related information together. When someone reads that chunk, they should understand the concept without missing critical context. In other words, a chunk should always follow the logic of the document, not just its length. But many people assume that the smaller the chunk, the better. Is that really true? So that brings us to the next question. What makes a bad chunk? Let's imagine a policy document says employee may carry forward unused leave. Now suppose the very next sentence says only after manager approval and subject to company policy. If these two sentences are stored in two different chunks, the retrieval system might retrieve only the first one and the answer becomes incomplete. That incomplete answer often becomes the incorrect answer. So chunks that are too small can lose context. But if smaller is not always better, then should we simply make the chunks much larger? So that brings the next question, how large should a chunk be? Now imagine the opposite. Suppose every chunk contains 10 pages. Context is preserved, but retrieval becomes less precise. One chunk may contain leave policy, travel policy, benefit, remote work guidelines, all mixed together. The system retrieves a large amount of information, much of which has nothing to do with user question. This creates unnecessary noise, and more noise usually means lower retrieval quality. So effective chunking is really about balance, not too small, not too large, large enough to preserve meaning, small enough to remain searchable. But even if we choose the right size, another challenge is, what is chunk overlap? Imagine one paragraph ends with, employees may work remotely for 3 days per week. The next paragraph says, the policy applies only after completion of probation. Now suppose these two paragraphs fall into different chunks. The relationship between them will be lost, right? To solve this, many rack systems use something called chunk overlap. Instead of ending one chunk and starting the next one completely fresh, the system repeats a small portion of text in both chunks. This preserves continuity. Important context is less likely to disappear at the boundary, so overlap always helps maintain meaning across chunks. Now one final question remains. How do engineers decide the right chunking strategy? Is there one perfect chunk size? The answer is no. There is no universal number that works for every application. The ideal chunk depends on the type of document, the type of question users ask, the retrieval strategy, the language model being used, the balance between accuracy, speed, and cost. That's why chunking is not just text splitting. It is an engineering optimization problem. In fact, two organizations may use exactly the same documents, the same vector database, even the same LLM, yet produce very different results simply because their chunking strategy is different. Experienced AI engineers often say good retrieval begins with good chunking, and now we should understand why. But our journey is not over. Even after we have created perfectly designed chunks, there are still just text. Computers don't understand the language the way humans do. How does AI recognize that vacation policy, annual leave rules, and paid time off may all refer to the same similar ideas? Even when the exact words are different, that takes us to one of the greatest innovation in modern AI, embeddings. So, what are embeddings? Now that we have broken large documents into meaningful chunks, another question naturally arises. The chunks are still just text. So how can a computer search them intelligently? The answer lies in one of the greatest innovations in modern AI, embeddings. But before we understand embeddings, we first need to understand something even more fundamental. Can computers understand language? Humans understand meaning. Computers do not. A computer does not understand English, Hindi, or any other language. It only understands numbers. Everything inside a computer, text, images, audio, video, is ultimately represented as numbers. So if AI wants to process language, it must first convert language into numbers. That naturally leads to the next question. How can different words mean the same thing? Consider these three phrases: vacation policy, annual leave rules, paid time off. These words are different, but the underlying idea is almost the same. Now compare them with company logo color. As human, we instantly recognize that the first three are related and the last one is not. But how can a computer make the same distinction? This is exactly the problem embeddings are designed to solve. So next question is, what does an embedding actually do? An embedding is a numerical representation of a meaning. It does not simply represent the words, it represents the underlying idea. Every chunk of text is transformed into a collection of numbers. If two chunks express similar ideas, their numerical representation becomes similar. If their meanings are unrelated, their numerical representation becomes very different. In other words, embeddings allow computers to compare meaning rather than wording. So next question is, why are embeddings one of the greatest innovation in modern AI? Traditional search works by matching words. Embedding work by matching meaning. A search for refund policy may successfully retrieve a document discussing returns even if the word refund never appears. The system is searching for similar ideas, not identical keywords. The capability is called semantic search, and it is one of the foundation of modern RAG system. Now every chunk has been converted into a numerical representation of its meaning. But a large enterprise may contain millions and even billions of such embeddings. Where they are stored and how they can be searched in milliseconds. That brings us to the next section of RAG Mastery Playbook, where we will be going deep inside of vector databases. If you have been able to understand the concept we have covered so far and enjoying this journey through RAG, consider subscribing to EdgeTalks, clarity that moves with you.